So quick review from yesterday. Okay, we went over velocity versus time graphs yesterday. Then we did some problem solving to do with both position versus time and velocity versus time graphs. But we want to quickly review what we can get from velocity versus time graphs. Obviously, what we can read directly off the graph is velocity and time. Okay, we can also calculate acceleration. We can calculate acceleration because that's the rate at which velocity changes over time. And anytime we're looking at the rate of change of y over the rate of change of x, we're calculating the slope. Okay? The change in y divided by the change in x is always going to give us the slope of the line. That's why on this type of a graph, okay, when we're looking at slope, which is m equals y minus b over x, what we're really looking at is one velocity minus another velocity divided by time, which is the formula for acceleration. Okay, they're the same thing. The other thing we can calculate from velocity.
So when you have the graph that goes like the curve for acceleration when it continues to accelerate, does that constitute the acceleration over the entire curve? Or?
Yes. So if this graph were to be a curve, and it could be, it means the acceleration is not uniform. Okay? In this one, the acceleration is uniform because the velocity is changing by the same amount every time interval. If it was a curve, it would mean it's non-uniform or exponential acceleration. And yes, if I went VF minus VI over T, it would give me the average acceleration. It wouldn't really be a meaningful number given the relationship going on in the graph. Yeah. Okay. If I wanted to calculate the displacement of the object, okay, in this graph, then I still want to use this formula. Average velocity equals displacement divided by time. Okay, but I want to calculate displacement, so that means I'm going to take average velocity and multiply by time. If I have a graph where the object is traveling at a constant speed, that's pretty easy, because its constant speed is also its average velocity. Everybody okay with that? Right? And I just take the average velocity and multiply by time, which is the area of that rectangle. Okay. If I have a graph like this one, okay, then I have two shapes. Okay, I have an initial velocity on this graph of 4.14 meters per second. Okay, which means if the object didn't accelerate but traveled at 4.14 meters per second, it would travel a displacement equal to this blue rectangle. Okay. And I would calculate that simply by going the base, which is the time in seconds, multiplied by the height, which is the initial velocity, 4.14 meters per second. Everyone all right with that? Okay. Then, during this part of the graph, okay, this triangle here, what's happening to the velocity? It's accelerating, so the velocity is changing. In this case, it's increasing. Right? I still can use this formula. Average velocity times time equals displacement. The velocity changes from this value to this value, which means the average is where? In the middle. Okay? Now that's true as long as it's uniform, a lot. Okay? So I would have, this is my average velocity. Well, okay, that would be, that number, average velocity, would be half of this number, yes? Or half of the total height, okay? Which means I'm still calculating the area under the line, okay? Because average velocity is the height divided by 2, and the time is the base. Okay, so calculating the area under the line on a velocity versus time graph is always going to calculate displacement because it's taking those two things and multiplying them together. All right? Okay. So we ended off yesterday looking at this graph. Okay? People were a little thrown by it because it had a lot of different shapes. 9 to be exact. We had to calculate the areas of all of them Okay, recognizing that each part of the graph kind of represented a different kind of motion. All right, so the first 2 seconds of this graph, the object's doing what? Nothing. Right? It is traveling at a constant velocity of 0 meters per second. In other words, it's not moving. Right? Thus, there's no area to be calculated here because the line is directly on the x-axis. At time 2 seconds, the object accelerates backwards at a constant rate from 0 meters per second to -3 meters per second. Would it cover a displacement during that time? Yes, it would. Okay, that displacement would be equal to the average velocity between 2 and 5 seconds multiplied by the time, 3 seconds. We're all right with that? So the average velocity, if I accelerate from 0 to -3, would be 1.5, or half the height of the triangle. Right? So I'm going base times height divided by 2. So the height over 2 is 1.5. Okay, multiplied by 3 on the base. This is going to be -4.5 meters. Okay, -3 times 3 is 9. 5 by 2 is 4.5. -4.5. Why is it negative? Let's go backwards. Yeah. All right, then at time 5 seconds, the object starts to accelerate in a forwards direction. It's not actually moving forwards yet, but it's accelerating in a forward direction.
So you're saying it's accelerating, but when you show that on a graph, doesn't it have to have a curve of this?
On a position time graph. This is a velocity versus time graph. So it's always important to make sure we remember which type of graph we're dealing with. Okay, so during this second, between 5 and 6 seconds, the object accelerates from -3 to 0 meters per second. And again, I can calculate its displacement by taking the average velocity and multiplying by time. So base of 1 second, height of -3, 3 times -3 times 1 is -3, divided by 2 is 1.5. Right, so that triangle there has an area of -1.5 meters. All right, then the object starts to move forwards. So at what time does the object actually change direction on this graph? When it crosses the x-axis. Okay? During this entire part of the graph right here, okay? During this entire part, it's accelerating forward. It only starts moving forward when the velocity becomes positive. And that happens at time 6 seconds. All right. So I've got this little triangle here that I have to calculate for while it was accelerating and moving forwards. Okay? It has a base of 1 second and a height of 2 meters per second. 2 times 1 is 2, divided by 2 is 1. All right, so that little triangle represents a displacement of 1 meter. Then the object travels at a constant speed of constant velocity of 2 meters per second forward for the next 5 seconds, right? Yeah. Okay, what's 2 times 5? 10, right? I just calculated average velocity times time. So this is 10 meters in here. All right, then I got this little triangle where the object is now accelerating backwards again. Okay, still moving forwards, but accelerating backwards. Okay, the base is 1/2, and the height is 2. Right, so 2 times 1/2 is 1, divided by 2 is 1/2. All right, so that little triangle there has an area of, has a displacement of 0.5 meters.
So is the 0.5 meters, is that accelerating backwards?
During this section of the graph, the object is accelerating backwards. Okay, its velocity is becoming more and more backwards.
Okay.
Right? It starts out moving forwards, but it's slowing down. Right? It eventually reaches a speed of 0. And then begins to move backwards at an increasing rate. Yeah. All right. So now we've got this other part where now we're not only accelerating backwards, but we're moving backwards as well. Okay. A very tall, very skinny triangle. It has a height of -6 meters per second and a base of 1.5 seconds. All right. So 6 times -6 times 1.5 is -9, divided by 2 is -4.5. Okay, the other shapes I have are here. Okay, in this section of the graph, the object is accelerating forwards, still moving backwards, but accelerating forwards. Okay, this triangle here has a height of -4 and a base of 2. Right, so -4 times 2 is 8, divided by 2 is -4 meters. I have this rectangle right here that has a height of -2 and a base of 4, so this is -8 meters. And then I have this last section of the graph where the object is accelerating forwards and coming to a halt. Okay, so the height of this triangle is -2, the base is 1, so -2 times 1 is -2, divided by 2 is -1 meter. All right, and then that last little bit, it stopped for 1 second. Okay, everybody with me there? All right, now, was any of that math overly difficult? No, but there was a lot of it. Okay, and we had to recognize what was the object doing. And guys, you may have noticed it took me a really long time to do all that, but that's because I was talking myself through it. Okay, I was saying to myself, okay, here's what the object's doing during this part of the graph. It's always good to do that. Okay, recognize here's what's going on, and that's what this means for me in terms of math. Okay. All right, now that I've got all those displacements, what do I do with them? I add them all together. Okay. So we've got -4.5, okay, plus -1.5, plus 1, plus 10, plus 0.5, okay, plus -4.5, plus -4, plus -8, plus -1. All right, so total displacement is -12 meters. And that should make sense. I mean, if I look at this graph, I definitely spend more time going backwards than forwards. Okay, so it makes sense that I should end up behind where I started. Okay. All right, so that's the displacement over the whole trip. Okay, next thing asks, what's the average velocity over the whole trip? Have I done most of the work for that already? Yeah, I just calculated the displacement, which took forever, right? How long does this whole trip take? 20 seconds. All right, so -12 divided by 20 should give me 0.6, right? -0.6 meters per second. All right, and then last thing, okay, what's the average acceleration between second last thing, average acceleration between 14 and 20 seconds. All right, so time 14 seconds is right here, 20 seconds is right here. All right, acceleration is VF minus VI over T. I can't calculate the slope here because there isn't one single line to use. Right, so then I have to use this formula. What's my final velocity? 0. What's my initial velocity? -6 divided by 6 seconds. It's only between 14 and 20, right? So 6 seconds. So 6 divided by 6 is 1. 1 what? Meters per second squared. And acceleration is a vector quantity. After all, we did say several times we're accelerating forwards during this part. That means we have to put the vector on there. Okay? It doesn't actually anywhere specifically say forwards, so I put a positive on it. Okay? Your answer should always match specifically what's in the question. Okay, and then the last thing is average speed. Again, I've done most of the work for that. I do have to change one thing though. I want to find average speed. I need total distance divided by total time. I found total displacement. Okay. I just add all those numbers together, ignoring all the mixtures. Okay, so if I do that, okay, so I'm going to go 4.5 plus 1.5 plus 1 plus 10 plus 0.5 plus 4.5 plus 4 plus 9. All right, so my total distance traveled is 35 meters. Divide that by 20 seconds, 1.75 meters per second. My average speed over the whole trip. Okay? Now, obviously, that one is a lot of steps. Okay? On a unit exam or a quiz, I would probably not give you one that had 9 sections for you to deal with. Okay? I could ask the same question using something like what was on our quiz today. Okay? I could easily give you a graph that had that same shape where we went like this and just made it a velocity versus time graph. So I think this was at like 1 second. Okay? This was at, say, 2 seconds. This was at 5, and this was at 6, something like that. Okay? We can say that this was 20. This is 40. Okay? So if I have a velocity versus time graph that looks like that, okay? This is time in seconds. Okay? This is meters per second here. Could I calculate my total displacement? Sure could. Okay? The way that makes this quick is if you can use as few shapes as possible. Because there's ways to do this that involve way more shapes, and there's ways that involve less shapes. Like, for example, I would make a rectangle that goes all the way across the bottom. This triangle, this rectangle, that triangle. I would ignore all of that, and I would just do those shapes. Okay, less work than finding this square, that square, and they could all be calculated in one step instead. Okay? All right, so if we're looking at the total displacement here, for the rectangle it would be 6 times 20, which is 120 meters. Okay, this triangle here has a height of 20 and a base of 1, so 20 times 1 is 20, over 2 is 10. Okay, this rectangle here has a height of 20 and a base of 3, so it would be 60 meters. Okay, this triangle here is the same as this one, so it'll be 10 meters. I add all those up, so 200 meters. Okay, would be my total displacement. That's probably more like what I would ask on a test, much fewer steps. Okay, it still tells me you know how to do it, but it doesn't take very long. Okay, so I want to keep working on those graphing questions from yesterday. I think a few people had gotten to these ones here. Okay, so 5 shouldn't take you very long. Okay, especially if you really like just look at it and recognize kind of the key things to that one. 6 will take you a little. 6 is like 4. Okay, there's like 10, 12 sections in that or whatever it is. Okay, so that one will take you a bit longer. All right, so let's have you working on those. I'll make that a little bit bigger, but it's probably a good idea to just have it open on your phone. I can't make it fit with 125. Okay, and I'll go over those here in a few minutes. Okay, let's be working on those for now. Okay, so on number 5, we can save ourselves a lot of time if we look carefully at the shape of this graph. Okay, because it can save us a ton of calculation. What I mean by look carefully at the shape of this graph, I mean, does the part that's below the x-axis look identical to the part that's above? They are. Okay? That means then that it spends just as much time and goes just as fast backwards as it does. If you do that, where do you end up? Back where you started. So you can say the displacement is 0 without actually doing any calculating. Okay? You can just look at this graph and know that the area here, okay, this rectangle and that triangle are exactly the same as this rectangle and that triangle. Whoops, sorry, I do that. No. If I did that way, it would not be true. Okay? Everybody all right with that? Okay. Now, for average acceleration between 5 and 15 seconds. So at time 5 seconds, we're moving at what speed? -8 meters per second. At time 15 seconds, we're moving at +8. All right, so acceleration equals Vf minus Vi over t. So that's going to mean 8 minus -8 divided by 10 seconds. All right, 8 minus -8 is 16. Okay, divided by 10 is 1.6 meters per second squared in a positive direction. Okay? I mean, during that time, it is definitely accelerating in a positive direction. That's why it ends up moving in a positive direction eventually. Okay, this question's not on here, but at what time does the object actually start moving forwards? 10 seconds. All right. Then for C, what's the average speed over the whole trip? All right, now I actually do have to calculate the areas under the line. But again, I can save myself a fair amount of time knowing that this rectangle and that rectangle are, okay, same for the triangles. All right, negative 8 times 5, 40, and this triangle is half that size. Again, saving myself some time, right? I've got 60 and 60, which is 120 meters divided by 20 seconds, okay, gives me 6 meters per second. Right? So there's always ways to kind of save yourself a bit of work if you can visually recognize some things in a question. All right, any other questions on that one? How are we doing on number 6? Just starting, it's going to take a while, it's got a lot of steps. Make that bigger in case you're using this one. All right, so the first part of this question wants to know the acceleration between point A and point B. All right, so acceleration, remember, is, whoops, right. Acceleration is Vf minus Vi over t. Okay, so that means taking our final velocity, which is 20, subtracting our initial velocity, which is 0, so 20, divided by the amount of time, 2 seconds, getting ahead of myself, it's 10 meters per second squared. All right, now remember that in part B, you are only asked to calculate the displacement between A and E, not all the way to the end. Okay, you only need to go this far. Okay, so do we just need to go over it so we can see where we're going on? That's kind of what I thought. All right, so we need to identify, okay, what's going on first. In part A, obviously, it's accelerating. Okay, between B and C, it's staying at the same speed or velocity. Then it's accelerating again. Then it's traveling at a constant velocity. So during the time where it's traveling at a constant velocity, okay, I just need to find the area of like the boxes. And for the other parts, I need to find the area of the triangles and take the average velocity during the acceleration. So in other words, I've got a triangle here that I need to calculate the area of, a rectangle to calculate the area of, and this triangle and this rectangle. You may have drawn it differently, and if you did, that's fine. We're still calculating the same amount of area here. We should get the same answer. Okay? We should. You are obviously doing something wrong, because there's no way that my answer could be wrong. Ever. Okay? All right, so let's have a look at the calculations here then that we have to do. So during the first part where it's accelerating, I want to use the average velocity, which is half the height of the triangle. Okay, so we'll take 20 times 2, which is 40, okay, divided by 2 is 20 meters. Then I've got this big rectangle where it's traveling at a constant velocity of 20 meters per second for 6 seconds. Okay, so 20 times 6 is 120 meters. Then I have this triangle that has a height of 20 and a base of only 1 second, so 20 times 1 is 20, over 2 is 10, okay? And then I've got this box that has a height of 20 and a base of 3, so that's 60 meters. All right, 60 plus 10 is 70, plus 120 is 90, 190 plus 20 is 210 meters. Okay, everybody with me there? If you drew different shapes, you should still get the same area. Okay? Just you're going to do probably more calculations because you would end up with more shapes. Okay? We're trying to limit the number of calculations you do. All right, keep going on that one. You still have to find acceleration between F and G, which is super easy. And the average velocity between A and F. Remember that average velocity is total displacement over total time. That should help you a little bit on that one. Okay, and then the total distance traveled. I would keep all those numbers we just did there, okay, and find the rest of it in order to get that. Okay, I'll give you a little more time. All right, so if we're looking at this, the rest of this question here, okay, finding the acceleration between F and G is a one-mark question. What's the acceleration? Zero. It's a flat line. The velocity is not changing between F and G. Okay, the average velocity between A and F. So I have to add on a couple more shapes here, okay, to get the total displacement between A and F. So this box here is 2 on the base and 20 high, so it's only going to be 20 meters. And then this box here is 20 high by 2 wide, so it's 40. So I'm adding on another 60 meters to the 210, okay, giving me 270 divided by 10 seconds, which gives us 27 meters per second. All right, and then finding the total distance traveled means finding the last couple of shapes. Sorry, that's not what we want to do. Okay, we want to go a rectangle that goes all the way to the end, and then this small triangle here. Okay, so this rectangle would also be 40 meters, and this little triangle is 10 times 1, so it's only 5. Okay, when you add all those up, you get 315 meters for total distance traveled. What's that? Well, I am. But by now, I've done this one enough times that I'm sure all the answers are.
I'm not kidding. So like a couple of years ago, like 2 years ago, I was just like,